So I invite all the participants to take a seat. We will start in a few seconds, I would say, not minutes. And to please also occupy the seats in the front. No one will bite you, I promise. This is a very friendly project. Okay, so if I have the okay from Eleonora to start and from the streaming. Okay, perfect. So, good morning, everyone, and welcome to Grenoble. Welcome to the VERSAPRINT Industrial Workshop. It is a pleasure to give the opening today. So I'm going to present myself for those who don't know me. So I'm Evelina Castellana. I'm Operations Manager at LEITAT for an environmental engineering SME based in Spain, in Valencia. And I'm here today with many of my colleagues, Marco Bianchini, Zach Morin, Eleonora Ferrarelli, and Michel Mirea, who I really thank you that helped me organize this event to close the VERSAPRINT project, and also, of course, the coordinator, Lisa Lu, Gracia, for supporting us in all this project, and to bring the project to this very important milestone, which is the end, the closing, and showing also all the results that the partners together reach. And I also want to thank, of course, all the participants, both in person and online, the partners that made this a reality. And yes, and thanks to their work, we can be here today to showcase all the important results that we have reached up to this point. So I'm going to briefly present you the agenda for today. So you will be even more excited to be here today. Oh yes, well, we can start from the agenda and then go back to the other one. So during this session, the opening, I will hand the word also, of course, to CEA to give a warm welcome, and we will have also another speaker from an industrial actor from FEV. Then the first session will be dedicated to VERSAPRINT technological advancement. So we'll hear from some of VERSAPRINT partners. Very important moment, the coffee break, where you will have the chance also to network, to get to know yourself between you and the participants if you didn't have the chance to meet before. And then we'll have a second session dedicated to the clustering projects, so projects that are also working on VERSAPRINT topic, and that we have been working also during this year together. So thank you for all those projects to be here online and in person. Then, of course, we'll have the lunch, another good occasion to network and to get starting new partnerships and a new idea. We will also have a table outside where we'll have the coffee breaks and the lunch, where you can see the prototypes of VERSAPRINT. So I also invite you to see our expositions. And then we'll have two sessions in the afternoon. So the first one will be the cross-sector and sustainable deployment of printed battery systems for electrified mobility. So this will be dedicated to VERSAPRINT use cases. So we'll have the use case from the automotive, the aeronautics, the replicability to other applications, and then a part dedicated to battery sustainability presented by my colleagues. And then I think the most important, interesting part, I would say, the industrial roundtables dedicated to both the industrials, the policy, and also the clustering associations that there are also clustering activities around the VERSAPRINT and around the world of batteries. And I also want to give an information about questions. So after each session, you will have the opportunity, of course, to make questions to the speaker, either in person. I mean, we will have a microphone. I will pass it in the room. But also, if my colleague can share, yes, wonderful. Also online. So we'll use the Slido. You can scan this QR, connect directly to the to Slido, and you will see the questions that we will pose during the day, and also open questions. So use the Slido, but we'll also use the old-fashioned way, let's say, to put questions. So without any further delay, I will hand the word to the CEA representative, Florence Rouillon, on stage. Thank you.
Good morning, everyone. Thank you, Evelina. I am very pleased to welcome you here at CEA in Grenoble, and I thank you all the partners and stakeholders that are present here, and of course the persons that are also online. So my name is Florence Rouillon, and I am Deputy Head of Electricity and Hydrogen for Transportation Division here at CEA in Grenoble. Our division is a part of the CEA LEITAT Institute. We are about 300 people. As the name of the division suggests, we are working on two main different applications, batteries on one side and hydrogens. That means for us PEM fuel cells and low temperature electrolyzers on the other side. Before going on, I will just give you some few data about CEA. Since 80 years, the CEA has been committed in the European scientific, technological, and industrial sovereignty, towards a more secured and for present and future. And the CEA is tasked with guiding public decisions and providing the scientific and technical means that civil society needs to better manage major societal changes, such as energy transitions, digital transformation, and future healthcare, and also defense and global security. At CEA, we are about 21,000 employees, and we are organized in 4 big divisions. One is dedicated to national defense and security. Another one is dedicated to nuclear and renewable energies. And the third one is dealing with fundamental research activities, and the last one with technology for industry. The CEA has more than 700 industrial partners, and we collaborate also in hundreds of French and European projects. Just to give you an idea of our innovation capability, we have now more than 7,000 active patents in our portfolio, and we are also very proud to remain the world's most innovative public research organization according to the top 100 global innovators published by Clarivate in 2026. And as we are present for the 14th time in this ranking, note that the CEA is the only research organization to maintain such a level in this ranking, which evaluates more than 3,000 companies and research organizations worldwide. Inside the CEA Energy Division that I mentioned before, the CEA LEITAT Institute is located here in Grenoble and also in Chambéry, a little bit from some kilometers far from here. And it is a technological research institute specializing in energy transition technologies. Our research activities focused on a number of key areas like solar power, network management, storage, including batteries and hydrogens, and geared to energy efficiency and a circular economy. Our research encompasses diverse applications in the energy generation and distribution markets, transport and industrial processes, and also for the environment. At LEITAT, and particularly within our division, batteries play a central role in the energy transition and the decarbonization of our transport systems. And our battery platform designs the cells and battery systems of current and next generations. And we are working really all along the value chain, including simulation, modeling, and life cycle analysis. And our activities cover all of the value chain, as I mentioned before, from synthesis of materials, their implementation into components, the assembly of packs, system integration, right through the testing. And with all this concentration of resources and equipment, the platform is really a unique R&D tool in Europe. Just to go on with our roadmap, it is structured around several priorities. The first one is accelerating the electrification of transport, whether for light mobility, electric vehicles, or AVR applications. We want also to improve battery performances in terms of energy density, lifespan, and safety, and also to develop more innovative, flexible processes and designs that are compatible with large-scale production and for transfer to industry. The main challenges we are developing batteries that are more efficient, more durable, safer, and produced competitively in Europe. And in this context, of course, the VERSAPRINT project is fully aligned with our strategy. It illustrates our ambition to contribute to the emergence of new generations of batteries by exploring innovating technologies at intermediate stages of maturity. And beyond scientific and technological advances, this project is key importance for the development of a robust European sector, which is really essential for strengthening our sovereignty in the field of battery technology. In particular, VERSAPRINT allows to develop innovative manufacturing processes in 3D printing, of course, and scaling up of technologies. And the real strength, if I could say like this, the real strength of a European project like VERSAPRINT lies in creating close collaborations between all the stakeholders. This helps to build bridges between academic research, RTOs, and industry to share knowledge and jointly prepare for the transition for industrialization, which is precisely the aim of today's event. And the challenge of this final key stage of a project is really to transform promising results into concrete industrializable solutions. And that is why we need to answer the following questions during roundtable discussions organized today. For example, what are the remaining technical barriers? What are the challenges in terms of cost, processes, and scaling up? And how can we continue, of course, to collaborate beyond this project? So I wish you to have a good day with fruitful discussions, and we hope also new opportunities for future collaborations. And I thank you for your attention.
Thank you very much, Florence, for this introduction on CEA and for this very warm welcome. I now hand the word to, yes? No problem. So I'll hand the word to Lisa Lou Gracia. She's a project manager at CEA. She holds a PhD in chemistry from the KIT, and she has developed expertise in battery system and also LCA at CEA. As part of VERSAPRINT, she's the coordinator of the project, so she will give us an overview of this very interesting journey we are now closing. So thank you, Lisa Lou.
Thank you, Evelina. Sorry for this little change. We just wait for a small bug to be resolved with Johanna, so I'll go first. So again, thank you very much for being here. We are really happy that some of you could join us today so that we can show you the results of this 3 years of project. And we are also really happy to reach the end of this project on time. And if it's okay, then we can switch to the next. I do it myself. Okay, so my goal here is to make a small overview of the project so that we know you can picture what was the project about, but of course everything will be detailed all along the day, and the goal is that so each partner is here today. So if there is anything interesting for you or where you want to have more details, the goal is for you to discuss with them. So my goal is to only make a small overview of the project so that you know what it is about. So first of all, the project stakeholders. So who were we to work on this project, VERSAPRINT? Here you can see all the partners. So it was a mix between RTOs, academia, and industrial partners. And we had 3 years and 5 million of budget to work on this project. I will show you after on what. We also were advised all along the project by our advisory board. We tried to have also a diverse and varied advisory board where we could ask them questions all along the project, and they guided us throughout this project. And we are, VERSAPRINT here is also part of a cluster with a brother-sister project. And some of the coordinators of this project are also here today, if you're interested. And we built a cluster all together to help us disseminate our results and to have common results where we can communicate on this similar topic, which is so next generation battery systems. And by systems, we mean without taking care of the chemistry. So you will see that we take care of everything what is around the cell, but not the cell chemistry. So this is why we built a cluster together. So our project, the goal, as I said, was to develop and to work and innovate at system level. So the vision of our project was to develop building blocks, so like at component level and at different levels, so just around the cell, a bit higher to connect cells together, and a bit higher at a bit more higher integrated level. So we developed building blocks, and the goal was to develop next generation battery systems that are more modular. And by this we mean we wanted to develop building blocks that can adapt and be used for different applications, so that we can combine them in a different way, in an optimized way for a specific application. And also we used for this, we wanted to work on new processes like additive manufacturing processes, and especially 3D printing processes, to have more freedom and to innovate, because we developed building blocks at TRL 5. So it means that they are not optimized components, they are not ready components to be sold. So they are, it's only innovative components. And we used 3D printing techniques to have more freedom and to design the most innovative components as possible. So as I said, we had different levels. By this I mean that we developed components just around the cell. So for example, I will show you after, for example, a cooling system with micro channels that were 3D printed just on top of the cell, or sensors also to be printed directly on the cell surface. Then to connect cells together, we mainly worked on bus bars. And at module level, we worked, the goal was to work on the casing and to change the material from metallic to composite material and to decrease the weight by doing so. And we also worked on an exhaust gas management system, which we can discuss later as well, because it will be in the further presentation of Lionel. And to show you here our objectives, we had to work, and this was the same for our brother projects, as I said, from the cluster EU Ingenious. We all had to work on safety, performance, lifetime, circularity, and cost. So here you can see some of the examples, the concrete examples we had to achieve. So for safety, for example, we had to reduce the electricization risk. For performance, we had to increase the energy density. The lifetime, we had to increase the lifetime with specific numbers as well, to eco-design our components and to decrease their environmental impact and to reduce as much as possible the cost. So you will see later that this will be one of the main issues we had, because as we developed very innovative components, they are not optimized, and so reducing the cost was a compromise. I will not go into details. It's just to show you some examples of what we did. They will all be detailed in the further presentations. As I said, we worked on microchannels. There you can see our sensors, 3D printed sensors. Here you can see examples, very different examples of bus bars that we developed. One that you can clip directly, so easy to dismantle. Here you can see a first life, second life, bus bars with multifunctionality that aims to be able to cool down through this little bridge here. And here at module level, you can see how we integrated all these components into real modules for different applications. This will be detailed later as well. And the system of the exhaust gas system, where our aim was to have no fire outside of the module when there is a thermal runaway event. So this we managed, and this is a really great result. So don't hesitate to come to us if you want to discuss it. Here you can see how we integrated it first into MIDI modules. And here you can see that we actually built real physical prototypes for different applications, so automotive, aeronautics, and for the waterborne, it was only simulated. And you will have objects there to see, and as well a generic module, a physical generic module. A small word as well. One goal we had also during this project was to develop a decision tool. This was done by the company ABI. The goal was to simulate a battery pack, and for this decision tool to tell the user which building blocks we developed to use for which application. So for example, if one application, aeronautic, needs very lightweight and high safety standards, then it would mean that we would pick this and that component. For a different application where performance is more important, that we would need this and that component. And then it would tell the user which combination of building blocks can be used. So this we also did during the project. Some challenges, because we are at the end of the project, and I think it's also important and interesting to see what worked and what was a challenge for us as a European project with 10 partners and with a limited time, so 3 years only to target all the objectives we have. And just quickly for you to know, one of the main challenge for us in the beginning of the project was to purchase cells to work on. So as I said, we don't develop cells ourselves, we had to purchase them. And this was a real challenge to find European cells. Those technologies, we also encountered challenges. So the sensors, printed sensors, so we do have great results, but not optimized yet. And as I said, we also wanted to work with the team of LEITAT, and they are here today if you're interested to discuss this as well. So to 3D print SRP, so self-reinforced polymer. As I said, the goal was to increase the energy density, so to decrease the weight. So we wanted to work on composite materials. And this polymer was successfully made, but the properties were not good enough to be used as casing. So it's also interesting results. So if you are interested, that will be with the team of LEITAT. A small word as well on sustainability. So Marco here will be here all day for you to discuss this with him. We also had high objectives in terms of circularity during this project. So where we eco-designed, and you can also discuss anytime how we did this. And we used a streamlined LCA where we evaluated and assessed the environmental impacts of all the technologies we developed, and as well of the integrated modules in the end, to see in reality what would be the impact. Do we decrease or not the environmental impact? I'm going to pass on this. This was our objectives and what we believe we achieved in terms of alignment with the European Circular Economy Action Plan 2020. And last word on today. So today is part of our effort of dissemination. As we are a European project, we have to disseminate our results and communicate and share and create next projects and next collaborations to continue working on them. We have scientific papers that were published during the project. If you're interested, don't hesitate to scan this QR code. It will bring you to our community on Zenodo. So this is a public community where you can see all our datasets, not all our datasets, but the public datasets, and all the papers and anything that is public. So we do have a lot of results and data, so 24 in total for the moment, more to come on Zenodo. And yes, if you have any question on this, don't hesitate to look there or ask us, because this is also an interesting part of this project. And this event today is to show you what we did, basically. And with this, I will leave you here with the next sessions. And I'm really happy that you came today. Don't hesitate to come to us. So you will see all along the day the different presenters and the partners from the project. So don't hesitate to come to us for any questions, or if you are interested to know more in a specific technology, and we will guide you towards the correct person. And I wish you also a very happy day and fruitful discussions.
Thank you very much, Lisa Lu, for this very complete and very interesting insight on VERSAPRINT project. And now, yes, it is time for our industrial partners. So Dr. Johanna Helm, she studied mechanical engineering at RWTH Aachen and earned her PhD in laser microwelding at Fraunhofer ILT. She now works at FEV Europe as a technical specialist for battery joining processes, supporting development and prototyping for automotive industry. In VERSAPRINT projects, she leads the activity related with the prototype development and testing. So I welcome you on stage. Thank you. You can use this to switch the slides. So here you have your notes, right?
Yes, exactly.
Okay, thank you.
Okay. Hello, everyone, and welcome to the industrial workshop. So I have the honor today to present the keynote speech. Sorry for the trouble in the agenda, but now we are all ready to go. So I was asked to talk today a little bit about the future of battery manufacturing, industrial trends, and research synergies. The picture you see behind is how AI visualizes the future of battery manufacturing. For me, it looks more like a train station, I must admit, but yeah, let's see. So maybe a few words about FEV, the company I'm working for. So FEV is a globally operating engineering service provider for the automotive industry. They started in the 70s doing the development for combustion engines, mainly for automotive, but also for commercially for commercial vehicles. Now we're moving further and further towards electrification. This is also what you see in the company. Of course, I'm also working in the battery department. So nowadays, also our main customers are still coming from the automotive industry, but there are also expansions of the product range into aerospace, trains, marine applications, and of course also currently defense projects. Now, I thought about, okay, what are currently the main challenges for the automotive battery pack development? And you can divide it probably into the three main parts of the pack for the automotive industry. This is the cell level, the module level, and then the pack level. This is also what Lisa Lu already addressed in her speech before mine. So let's talk a little bit about these main challenges that we are facing currently. So on the same cell level, we're talking about performance trade-offs, for example. So this is energy density versus power capability, lifetime, fast charging. You will never find the optimum for all of these factors regarding your application. So there's always a trade-off. You have to think about, okay, what is very important for my specific application. Talking about cell quality or variability, of course, everyone who has of you has tried to contact cylindrical battery cell knows about the manufacturing tolerances of these cell type, for example, but we are also talking about coating quality. Then the thermal behavior of the cell is very important. So what is the heat generation during operation? What are the cooling requirements of the battery cell? We've got safety or abuse tolerances. Talking about internal shorts, the gas generation during thermal propagation. We've got overcharge robustness of the battery cell, for example. Then the batteries undergo material degradation mechanisms. Lithium plating, probably the most famous of them all. And especially if we're talking about the current EU battery regulation, we're also talking about sustainable material sourcing. So sourcing the raw materials, the recycling of the materials after cell life, and of course also the CO2 footprint of the battery cell. Then talking about the module level, of course we've got the mechanical robustness of the battery, of the module. So how do I design my module that it withstands the vibration? This is, of course, different if we're talking about an automotive application or if we're talking about a plane or a ship. Then we have also the crash loads and swelling compensation. We've got the cell interconnection technology. So what is the welding quality like? What kind of connection do I want to use? What is the bus bar design in this case? We're talking about thermal interface design. So efficient heat spreading within the module, thermal interface material applications, sensor integration, all this is very important. The uniformity of the battery module also plays a role. So how is the voltage distribution within the module? How is the temperature distribution within the module? How do I guarantee the balancing within the module? Then manufacturability. So how do I guarantee an automated processing in my manufacturing site? And of course, very important, the safety concept integration. So fuses, electrical fuses, thermal fuses, current interrupters, for example. Then, of course, we've got the pack level. Most important, probably the thermal propagation prevention. So any barrier design within the battery cell or the battery pack, the venting concept of the battery pack, coolant concept, very important. The structural integrity of the pack, crash behavior, intrusion, repairability, We are also talking about the high voltage integration, so electromagnetic compatibility, isolation, BMS, of course, always a very important topic, and system level energy management. So how do I optimize the range of the battery pack? What are my fast charging capabilities, load cycles of the pack? And then we've got durability and lifetime of the pack. So what are the road cycles? How do I deal with environmental conditions, salt, moisture, etc.? And sustainability and recycling. How do I dismantle my pack after the life? Is there a second life application? And what about the carbon footprint? So there are a lot of challenges, as you see, in the pack development facing. This is obviously not only true for the automotive industry, but all these topics can be summarized under performance, lifetime, safety, and circularity. And this is what Lisa Lu just addressed. So these are also the main topics for VERSAPRINT. And especially if you want to integrate this in the automotive industry, where there's always a super high cost pressure, all the applications and everything that you are developing needs to be cost effective, otherwise it has no chance to find its way into the real application. Then I have one slide maybe to also give a little bit of a future outlook. This is also a slide that was completed by colleagues of mine. It's based on the data that was collected by our company. You see on the x-axis the cell energy density, and on the y-axis the system energy density. So what this graph shows is how well I integrate my battery cell into the system to gain the most energy density on system level. So if the dots are moving further to the right, this is a cell optimization topic. If it's moving further up, this is a pack integration topic. And what we currently see is that that battery packs that are currently state of the art are reaching a VCTP. So this is the volumetric cell to pack ratio. So they're reaching a VCTP in between 30 to 60% basically. And I want to point out two areas here. The first one are the green dots. These are all LFP cell-based pack integrations. And you see that the LFP cell has a lower cell level energy density, but they are reaching higher VCTP ratios. This is due to a reduced system level TP measure. So you need less TP measures in the pack to make it safe and to make it ready for the market. So in this way, the VCTP ratio rises. And the other area that I would like to point out is the one that is circled in red and marked with the prologium concepts for solid-state batteries. So everyone's talking about solid-state batteries. Prologium is a company in Taiwan developing, these are semi-state, solid-state batteries. And FEV developed a few concepts with different cell types, and you see that the cell energy density is much higher of these the cell types. So we are reaching quite well also VCTP ratios. So this cell technology has probably a very promising future because it's also meets the target of the safety, the lifetime, circularity, and also the performance of future battery packs. Okay, this is the black slide. So thank you very much for listening. And I hope you enjoy the workshop today.
Thank you very much, Johanna, for introducing an industry point of view. And we're ahead of 5 minutes. Wonderful. So that we can have some buffer time, but don't take advantage of it. So I now hand the word to my colleague, Marco Bianchini, who will be the moderator for session 1. So thank you very much.
Hi, everyone. Thank you, Evelina, for the introduction. It will be my pleasure to introduce you then to this session. Again, from Lomartov team, my name is Marco Bianchini. I'm also a senior engineer and I've been working on this project since the very beginning. So it's a pleasure for me to introduce you to this session where we are going to showcase our technological advancement in terms of the building blocks that you already heard about. So we will start from the cell level building blocks, moving up to the outer shell, so passing to the cell level, cell unit level, and then to the module level. So hopefully this session will help you understand how our solutions are being engineered to meet all these requirements from the industry, pretty much. So without further ado, I will introduce you to Javier Palmer. So Javier Palmer holds a PhD in material science from the Autonomous University of Barcelona, where he's been researching the chemical pathways for superconducting thin films, but especially since 2020, he's been a researcher at the LEITAT, where he focused on the surfaces and chemistries, especially in functional inks and advanced coating. So he was responsible for the cell unit level work package. And so let's give a warm welcome to Javier. Here you go. Just the green button. El verde por la slide. Creo que sí.
Okay. Thank you, everybody, and good morning. I'm going to start with technologies that were developed for the at cell level. That it's the first level in the VERSAPRINT system, and what technologies can be applied in these individual cells that to improve the thermal management in these cells. The first technology was this cooling circuit that can be printed directly on the cell surface, and that is the building block 1. And the other technology is this temperature sensor that also printed over flexible substrates that can be attached over the cell surface. This development of these systems has been carried out by LEITAT with the collaboration of CA for the simulations and validation of this cooling circuit model, RWTH for the TP test, and Lomartov for the LCA. The concept of this VV1 consists of this coating with embedded microchannels that are located between each one of the cells in the cell unit and the module to perform this active cooling. This coating is applied directly over the cell surface, and it's aiming for a thickness around 3 or 4 millimeters. These internal channels are 3D printed using a sacrificial ink. The shape of the channel can be easily adapted by 3D printing, and is embedded within these 2 layers of this material. This coating material was a challenge to select, and finally was decided to use one kind of silicone that is easy to mold by casting techniques to achieve the geometry we want for the coating, and can withstand high compressive forces, and can be easily detachable to ease the recycling. All these channels are later connected to the cell module For the configuration of this VB1, it started with simulations of the circuit performed by CA, of the pressure and temperature effects within the channels and their impact on the material, to select the optimal configuration and geometry for the circuit. Based on these simulations, the VB1 was designed, incorporating connectors for the input and output channels, and all the circuit design was adapted for the 3D printing and to obtain the final size and geometry of this coding. Here I explain briefly the process for the 3D printing of the channels. As this, the configuration of the channels have to be embedded between the two layers of the coating material. The ink that it's printed to print to the circuit has to maintain this structure during the silicon curing process. For this purpose, we selected a sacrificial thermorheological ink, which viscosity decreases with temperature. So at room temperature, it behaves like a gel, but once cooled, it liquefies, and it's easy to remove from within the channels. This ink was printed using a homemade 3D dispenser, which allows a precise control of the dispensed ink, and it's easy to adapt to different geometries and circuit and size of the. Once we have this system with embedded channels and the silicon current, we can empty the channels and mold the system for the VB1. The second technology was this temperature sensor for the VB2. It was designed with sustainability in mind. The goal was to create this sensor printed on flexible substrates to be easily attached to any surface, and using a water-based ink formulated with conductive carbon particles and bio-based additives. This carbon pigment presents a good performance to cost ratio and a high surface area of the nanoparticles to improve the wettability and coalescence, and presents a semi-metal behavior with some good sensibility to temperature. This ink was formulated to prevent flocculation, achieve good wettability, and obtain optimal rheological properties for printing by skin printing. And several configurations and geometries were devised to select the one with the best performance. Now, as for the results observed in the development, this cooling system was validated. We can obtain these circuits that can be adapted also for different types of cells, such as NMC and LFP. And the initial performance test demonstrated a cooling effect of 15 degrees compared to cells operating without this active cooling. We printed several amount of these cells to be validated in the model systems in the different end users. For the temperature sensor, it was designed using this sustainable ink, which water as the main solvent, and using bio-based reagents. This ink can be printed on these flexible substrates, and it can be integrated under the VB1. So for a complete thermal management of this cell. We observed that the ink exhibits negative temperature coefficients, meaning the resistance decreases with increasing the temperature. And there are some limitations for now at these sensors. It presents a working range between 5 and 95 degrees. We have some problems with humidity in the extremes of this working temperature range. So the main challenges, next steps for these technologies, the first one, and probably the more important, is the material that conforms the VB1. We need to look for new materials that are more robust. This silicone offers versatility. It's versatile, but it's easy to handle and can support high compressive forces, but it's a soft material and weak under puncture and shear stresses. And this also applies to the connector that needs to be more robust for the handling. Another key aspect derived for the LCA analysis is to select a product that not contain these platinum-based curing agents, so we can increase the sustainability of this device. For the case of the temperature sensor, the main challenge we faced was achieving a good performance using low toxic and bio-based additives and reactants, but we need to work to increase the stability and operating temperature range. This is a summary of the key explorable results. For the VB1, we achieved a TRL of 5. It can be adapted to different cell configurations, and it has a limitation for the printing process that it must be on flat surfaces, but it's flexible enough to be adapted to another circular, for example, geometries. And for the transferability to other sectors, it can be transferred to sectors that might need some type of thermal management, for example, on wearable electronics, textiles, robotics, and where we need this thermal managing integrated in these systems. For the sensors, we have still some room to improvement, so TRL it's a bit lower. They can be in any way attached easily to any surface, and we can be transferred to another sector similar to the VB1, where the use of more sustainable solutions it's a requirement. And I think, yeah, this is for my part. Thank you very much.
Right, thank you very much, Javier. I think it was already a very interesting presentation. As you noticed, these first R&D activities on Work Package 2, in our case, were dedicated to the development of these thermal management systems, which are very important in battery system, as you know, not only for safety issues, but also to extend the battery lifetime, which is a key point in sustainability, and we'll see also about this later on this afternoon. But now let's move to the second session. So let's invite our speaker on the stage. So it's Yannick Taschbach. He's a research associate at the Laboratory for Machine Tools and Production Engineering at RWTH in Aachen University. And so after completing his studies in automotive engineering, he's now working on the prototyping technologies while also pursuing his PhD in the field of additively manufactured forming tool for metal sheet application. So he will tell us all about this in his presentation on the VERSAPRINT cell units. Yeah, thank you. So let's welcome him. Yes, you have the green button here.
Yep. So welcome everybody. My name is Yannick, as introduced. I welcome you from Aachen. So RWTH, Institute for Production Engineering, and yeah. So today, as work package lead, we had the cell unit level. So what was our role? Together with CEA, LEITAT, and Lomatov, we concentrated on the cell unit. You can see here on the bottom right. So we had different topics. I think in the beginning it was very important to design this generic cell unit together with all the partners. And yeah, you can see which roles each partner had. So LEITAT did as well some multifunctional bus bars. Lomatov concentrated on sustainability aspects and assessment. And yeah, we are from my institute, we were involved in easy to dismantle bus bars, which we did by sheet metal forming. Yeah. Coming to the architecture of our cell unit, you can see it here in the bottom. We have 3 cells. We have connecting bus bars, and we have these gap pads in between, so the microchannels presented by Javier. So this is BB2, BB1 in between the cells. And as well the thermal sensors on top of each cell. This is the assembly process here. You can see first attach the thermal sensors on the cells, stack the cells together with BB1 in between of the cells, and then close the housing with the compression plates. And yeah, on top here for BB1 you have as well another top plate having the connectors in place. Yeah, in the end you can see this MIDI module here on the right with 3 cells connected with our easy to dismantle bus bars. You can see they have these single wires here. This is a laser cut, and the forming was made with our 3D printed forming tools. I have also some outside. You can have them in hand if you're interested in that. Yeah, next. So for the bus bars, we had 2 different BBs. So the multifunctional bus bars made by LEITAT. They were initially made from copper, but this didn't work. So we switched to aluminum powder, melted and 3D printed together. So as you can see here, so you have these single wire connections printed out of aluminum for the first, and on the right also for the second life cycle of the battery when you disconnect the single wires. Yeah, what is the multifunctionals here? You can see this is mainly the first and second life cycle application, and as well it's for cooling if you increase the surface. There were several different other concepts as well. So breaking these wires with an hexagonal screwdriver. This was, for example, another option here, but in the end it didn't do. It was not the best concept, and here we have only the best. So on the bottom, moving forward to my main topic, easy to dismantle bus bars. On the left, you can see what we have done at our institute. So in the top, you have this bowl hole concept where you cut off these wave structure, the wires for dismantling, and you can see only second life, but in the first life you have this bowl, so it's possible to laser weld the bus bars directly on the cell terminal again. On the second, this is a so-called H concept, where also it's what the main topic here is to halve the surface used for welding, and in the second life you can add another bus bar without losing connection area. And in the bottom another concept, very similar, half and half, and so the full surface of the cell terminals are used with very similar performance indicators here. And on the right here, another concept from CEA, using easy to disconnect, connectors. These are commercially bought, no self development. Only the bus bar is made from aluminum, and the connectors are welded in. So a very easy but also expensive solution. In the end, this concept is much too expensive for all the applications in this project. So we did no deeper research in that. So coming to the key research results, so also BB1 was part of the cell unit module, so that's why you can see this again here. So in the end, we had good performance from the cooling, increasing the homogeneity of temperature inside the module. I think that's a very good result here. On the other BBs here, you can see copper was not suitable, so aluminum showed very good results here, it's easy to dismantle by cutting these wires, and as well they can be used as fuses in the module. So if one cell is defect, you will not have a full thermal runaway of the complete module. Going down here to BB4, our bus bars, you can see we had these non-welded, they are made from Molex, these connectors here in the bottom, very heavy as well, not only expensive but also heavy. And on the right side you can see our laser welded bus bars made from sheet metal aluminum, very easy to form. We did it with 3D printed PLA made forming tools. And the function to dismantle, it's the same as in BB3. So the main challenges and next steps, BB1, it performed very well, but production process is still a problem. Increasing the size, etc. This is still a problem, and we were here only on cell unit level, and for a complete battery module, there will be needed more testing. For BB3 and 4, optimizing, as Johanna said, is always a problem for battery modules. So this is also a topic here regarding our bus bars. The optimal point for all the factors is not easy to find. So optimizing weight, cost, and performance, it's strongly connected to each other. And end applications, we are on TRL level 5 with our BBs, and for further research, we need some more applications in future. So coming to the key exploratory results, you can see again all my or what I have presented. In conclusion here, you can see BB1 efficient and homogeneous battery thermal management did very well. 3D printed copper bus bars. It was changed to aluminum. Easy to dismantle bus bars are also on TRL level 5, and they performed very well. In comparison to reference bus bar without these wire connections. What we did as well, as I said, forming tools made out of PLA. I did not write down here any TRL level because it's always different to design these tools. You have a lot of prototyping on that, so it works with good results. And in the end, also here these alternative solutions to welding. This was our Molex connectors built in the bus bars. I also did not write down any TRL level because we didn't just had this application, no further testing on that. So that was that from my side. Thank you very much for your attention, and see you later.
Right, thank you very much, Yannick, for these interesting presentations. So, you saw here, say, unit level, basically the main focus was on the development of these boost bars, which again are key, I think, to highlight what was the value proposition behind VERSAPRINT projects in developing a fully circular battery value chain. So it's definitely a key point that we try to address with this R&D work. And now moving to the third presentation of this session, I'd like to introduce you to Lionel Paoli. That he's a senior mechanical engineer and project manager at CEA, with an experience spanning from mechanical design and architecture for advanced propulsion systems and lithium batteries for a wide range of applications, including aerospace, automotive, and marine applications. And in this project, he was the work package leader for the development of module level innovation. So let's welcome Lionel. The stage is yours.
Thank you very much, Marco, to introduce me. So let's talk about the module level of this project. So what was our role in VERSAPRINT projects? First is to develop a generic module to integrate all BBs previously described today at small scale level, so just a module, not a battery pack in the world, allowing integrates all BBs in a representative packaging at the battery system, and also integrates all interfaces as electrical interfaces, fluids, and others, and sensors, and so on. This module and casing need to be versatile and flexible, and also to be compatible with evolving designs afterwards. And at the end, this platform, it's a real platform for the casing development for all application and specific industrial applications. So what are the key results regarding the generic module design? So here I will talk about a generic module in order to be a platform development for industrial partners afterwards. Which will have a presentation after my presentation. So here we can see a the specific module with all BBs, so we can see cells and between each BB1 with a cooling system printing between each cells, linked electrically with the two main BBs developed at easy to dismantle bus bars, or also multifunctional bus bars. We can see also the integration of printed sensors for temperature and hydrogen sensors. The main component with polymer and fire retardant casing, it is the main BB5, BB6, what I will present to you today. In 3D printing process, it's to integrate all components inside the safe case in order to manage the thermal management and all thermal propagation afterwards. And you can also see where we can spring a PCM coating inside the casing in order to manage easily the thermal dissipation during the performance of the batteries. So here we can see the real prototype during the thermal propagation tests, and with self-transposed polymer, lightweight self-transposed polymer design of the casing, and LEITAT have print this casing with PATG material, and we can see here a specific fire response of this casing. So with smoke outside, without any particles and without any flames. It's a very good result for our application, and is mainly due to the BB7 development and also the casing geometry. So we've done a prototype, manufacturing the prototypes, done several thermal runaway tests, and at the end we divided temperature by 2 during the thermal propagation. And just keep in mind, we do not optimize weight and cost during this first step, and maybe the industrial partner will add some evaluation and some information about these parameters. What will be the main challenge and next step for to develop the BB5, BB6, and BB7? So just to remind you that the BB5 is to develop self-transposed polymer, and LEITAT have done several materials regarding the self-transposed polymer, and there is some issue regarding the mechanical properties, and that's why we used PATG commercial material to print the final geometry casing in order to do the thermal propagation tests. So today we need to go deeper in R&D to process this kind of material with SRP, and specifically for the printability. It's not with a conventional process. Regarding the BB6, that's the main topic is to add some additive to enhance thermal or fire response, and we also need to go deeper to improve the mechanical properties at the end for this kind of casing. And for the BB7, even if we use for this application titanium, it's still be heavy and expensive, and we need to work on this another material maybe, or another geometry in order to be lighter at the end. And maybe one of the main direction that we can do is to multifunctionize, optimize the overall geometry integration inside the module. So let's talk about key exploitable results. So the 4 main exploitable results, it's a lightweight battery components. So here we have done a generic module that integrates all components, and it's a very low TRL because we use a material, a commercial material, and we need to go deeper in SRP process. And also to enhance the mechanical properties. But for the transferability to the other sector, yes, I think it's completely adaptable, but we need to go some research on it. Regarding the efficient exhaust gas management, yes, how you understood that it directly linked to the overall architecture of the module regarding the application, and we can easily adapt the geometry and the integration directly linked to the whole volume needed in planes, for instance, or automotive. But in this key experimental results for gas management, yes, we reach TRL5 also, and it's adaptable for various applications. Regarding the PCM, FR additive is also very easily adaptable, and just need to make a good trade-off between the fire response and the mechanical properties is the main issue today. And we reach also the TRL5. And in parallel, we made some simulation with RWTH in order to calculate and simulate modeling all thermal aspects during the thermal propagation on one cell, and that allow us to develop this kind of architecture with all components inside this generic module. That's a real platform in order to develop the application, industrial applications. And that's it. Thank you very much, and have a good day in this workshop.
All right, thank you very much, Lionel. I think we have been quite fast so far, so maybe this hopefully will leave more time for discussion, for you to ask questions to our presenters in the coffee break and in the afternoon then. Sorry. Before that, we'll have one more presentation. So I have the pleasure to introduce you to Michel Harre. He's a mechanical and materials process engineer, providing support to the SONACA group since 2002, and where he's also a department leader, and where his main activities are basically about the integration of new systems based on the different requirements into the aeronautics and aerospace structures. So let's welcome Michel Harre, which will tell us more about VERSAPRINT applications.
Thank you, Marco. Okay, so thank you. So the objective here is to present to you a dedicated application used prototypes developed through VERSAPRINT project. So as explained here, we have tried to use VERSAPRINT solution to our end application. Here, as you can see on commercial aircraft, you have some functionalities that we can electrify. Here we select a dedicated application for anti-icing system. So all the commercial aircraft need to be anti-ice during the flight for safety reason, to avoid ice around the wing during the flight in extreme condition. So as mentioned here, the objective is to decrease the size of the engine with integration of electrified solutions. So the objective here is clearly to integrate system inside the structure for de-icing functionalities, and then we need to put in front of some battery to provide sufficient energy to de-ice this structure. You have here a picture of what we developed on composite structure, okay, and then we can put titanium skin on the top of composite structure to optimize de-icing functionalities. So based on interesting results developed by the different partners, we select the different building blocks, and based on that, we work with also Festo and all the other team partner to develop this solution at module level, and for sure to do the job up to the upscaling phases. So as you can see here, we have developed and introduced select different building blocks, mainly focused on 3D manufacturing processes. Okay, and so that the detailed results on the left side, and you have the prototypes on the right side. So based on this module, for sure we have performed design and stress analysis to validate the mechanical performance at the module level, to be sure that we will have no major issue during mechanical testing campaign. Based on the fact that the casing was not SRP material, we take the decision to reinforce the internal structure of the at the module level to be sure that we will have no issue during shock and vibration campaign. So we perform for sure all the mechanical simulation in static, fatigue, shock and vibration. And in the meantime, we perform also a dedicated test campaign to demonstrate that we will have no issue at module level. Then we switch to with other partners, with RWTH also. We perform some simulation regarding the cooling activities to be sure that we will have no issue for the thermal management system, and we evaluate some key parameters for the cooling system based on 3D printing of the cooling device, and we perform a C-pillar approach for exhaust gas management activities with Felix at upscaling level. So we start different simulation at module level, and we upscaling this simulation up to the full aircraft structures. Based on that, as mentioned before, we obtained different key results. One focused on structural behavior in shock and vibration test. So we perform the solicitation and the test in different axes with relevant acceleration that we have in aeronautics procurement specification. And all this test was done in Belgium and fully in line with our expectation. The second key point, more focused on electrical KPI, was done with the FEV team, okay, where we have identified, we have performed some environmental tests, and you have a synthesis here of the main results. As you can see, on some point we are in line with the requirement, and for two dedicated points we are close to the target, but not in line with this. But it could be explainable, and we are happy with these results. So that's an important point also. And the last campaign was done by a CEA team, thermal propagation test. Here, as you can see, we have a lot of fire outside the structure, but it's in line with our expectation for sure. And it's a gentleman reminder here to be careful about the safety, potential safety issues that we can meet in service condition. So it was very impressive to see this test campaign, and it's clearly a strong reminder for us regarding safety approach, and to be sure that at the end, if we put this type of battery in our aircraft, we have to be aware and be careful about this dedicated point. Regarding the last step of our results is the upscaling phases. So we work to characterize the module level, and then we switch to the upscaling phases based on our end use case. And as you can see here, it's quite large and big solutions that we can provide here. And so, as you can see here, it's more focused on the sliding concept because we would like to develop a plug and play and plug and fly solution to be sure that we save time in service conditions. So the time is running in service condition, and for sure we need to reduce this time to be more efficient on the floor during one flight scenario. So based on that, we have developed different solutions regarding the venting functionality and regarding the electrical aspect. The objective at the end is to save time if we have to remove one module or one battery unit in service condition, to be sure that we can remove it easily during the flight. So that's the reason why we focused at this stage of the project. We are focusing to develop plug and play solution, because time and cost, it's a key parameter for us in service condition, and we need to develop solution for end user and for our customer in line with this target. So regarding the challenge, one challenge for us, we are not specialists of battery and cells, but for us, it could be interesting to improve the size of the battery cells to allow us to integrate it in a different location. So as mentioned before, it was integrated in the fuselage, but for us, we are quite confident on the fact that for our dedicated application, it will be better to put in another location. For the moment, the main limitation is the size of the cells itself. It's too big for us, comparing to the performance itself. So the objective and the next step for us would be to work on it and to improve the total mass. We are quite... So it's clear that all the building blocks developed in the framework of VERSAPRINT project is in line with our expectation regarding the target weight. But it's clear here, based on a quick calculation that we have done, that the battery module and the battery cells, it's the main contributor of the weight, in fact, and the objective is clearly to reduce that. Because to have 1.5 tons covering this functionality, it's a good starting point, but we are quite confident that we can reduce this total weight working at the cells level, because at the other level, as mentioned before, all the different building blocks based on the 3D printing solution and so on, it's in line with our expectation. So the next steps for sure is to work on the cells technology. Regarding the challenge, yes, the first movies, it's one big challenge for us, clearly. So it's very important for us. We are very impressive about these results, and to keep in mind that it remains a challenge for when we have this type of behavior inside the fuselage of the aircraft. It's not so easy to manage. So it's one major challenge for us, for safety first, for sure. And the second point is regarding the casing resistance. For sure, it was a very interesting solution with 3D printing processes. But for us, it makes sense to work on it, to select new material for self-reinforced polymer technology. Then we can decrease the structure in size, okay, with a similar mechanical behavior. And at the end, if we integrate more functionality on the same space allocation, the final printing, the final solution will be better for everybody with weight and cost saving development. Okay, regarding the exploitable results. For sure, we have two dedicated points to cover. The first one is regarding the development and modeling of thermal and gas management. We have done with all partners a very interesting job regarding modeling activities. So for us, it's a validated point. And the second point, as mentioned, regarding all the building blocks, it's clear that a lightweight and multifunctional solution has been developed. In the framework of VERSAPRINT project, we are in line with expectation. The only attention point, as mentioned before, it's at the cell level, and we are quite sure that if we improve that, at the end we will improve the final solution for our applications. Okay, coffee break now, it seems.
Thank you very much, Michel. I think it's very interesting to see what are the challenges, what is the industrial perspective on our R&D activities. Just hold with me before a coffee break. We'll just open the floor to questions. So if any of you in the room have questions, or if we might have online, we are here to answer them. Or everyone is eager to go for coffee, I suppose. See? Then it means I'm gonna free you and let's go for a coffee. Okay? So we'll be back at 11:15 with the second session, where we have Pier Padilla moderating. And so we'll be back at 11:15. Thank you very much.